types. So Donovan mentioned these in his talk. This will be a more basic talk, very specifically focused on algebraic data types and what they are and how we work with them. So it was my opinion that BFPG needed more introductory content, and the only way to make that happen was I decided to give an introductory talk. So I encourage you to do the same. We have some FP mega minds in the room, and I would love to see more introductory content like this. So I'll be talking about algebraic data types. So I'll give some quick historical context. I'll tell you about what they are and then how to work with them, and then show you all the fun we can have once we've got algebraic data types. So Donovan and Isaac have both said this is like where the FP gets good or something like that. So I think something like that. So there was a language in 1973 called ML. Nothing to do with machine learning. ML stands for meta language. No one ever calls it meta language. Everyone always calls it ML. This is annoying because machine learning is much more popular than meta language these days, 50 years later. ML introduced or popularized many great ideas in programming. It has a clean, concise syntax, which it doesn't monopolize that. But it introduced type inference. It has parametric polymorphism. Also, like generics, if you've done Java, so like when you have less than, greater than with a letter in the middle, yeah, something like that. And algebraic data types and pattern matching, which is this talk. So pattern matching kind of already existed in some Lisp dialects to some extent, but this is kind of where it got good, in my opinion. ML is kind of, if you were going to split functional programming into two camps, which I don't encourage you to do, but if you did, they would be Lisp things and ML things, and Haskell's an ML thing. So ML influenced a lot of languages. It has many direct and indirect descendants. So OCaml and F# are fairly direct descendants. I would argue Haskell is something like a great nephew of ML. And I claim, this is like super opinionated and we can argue about it at the pub later, I claim that languages today in 2023, 50 years later, that feel modern to you are the ones that are like ML. That's a massive claim. Let's argue about it, but not right now. So I'm going to start with some things you've seen before, and then we'll move into algebraic data types, which you may not have seen before. So you've probably seen enums if you've worked with C or Java or some other very popular programming language. We're defining a new type. We're defining it by cases. So if we're interested in playing cards, we're interested in suits. A suit is either clubs or diamonds or hearts or spades. So I could have a variable of type suit. Now I could say suit S equals diamonds, something like that. Right? I'm defining a type by different things it could be. So Boolean is another example. Enum bool, false or true. If we have suits, we also have ranks. So we have king, queen, jack, the numbers from 10 through to 2, and then ace. I've had to prefix all the numbers because enums need to start with an alphabetical character. So I'll just put R on the front after rank. There we go. So you've probably seen enums before. Maybe you haven't. Has anyone seen enums before? I've seen enums before, yeah. All right. Something else you've probably seen before are what I would call records. In C, you introduce them with the struct keyword. In some languages, you introduce them with a different keyword, such as class. So I'm saying a person is a struct which has a record is a thing which has some fields inside of it. So a person has a name, an age, and an address, and probably some more things, but for the purposes of the example, that'll do. And we were looking at playing card things before, so we could say a card is a suit and a rank. A suit being diamonds, a rank being queen. Queen of diamonds is a card. So a record is putting some things together to make a bigger data type. Something like that. I'm going to quickly introduce these same things in Scala 3 syntax, because I'm going to use Scala 3 for a lot of the talk. I use Scala 3 at work. I use Scala 2 more at work.
What type of the R's there?
Yeah, something, you know, I would be surprised if that was the most glaring error we come across. So pretend those are some different numbers instead of always 10. But we use enum keyword, and curly braces are old-fashioned. We hate them. We use white space and colon instead. That's cool. Yeah, that's a joke. Anyway, so that's how we define our two enums, something like that. And then a record, we use case class. So you can see that Scala really loves the case keyword and just wants to put it before everything, right? So a case class is how you do a record in Scala. So you give the names of the members and their types. So I've punned the type to be the name because I couldn't think of a better name. So a suit of type suit and a rank of type rank in a case class. So that's a record. These are enums. Now you know some Scala 3. Here's some more Scala 3. We can define a function. So if I have a person case class with a name and an age, they had an address before, but they've lost that, whatever. I can greet a person, which is a function that takes in a person. So I introduce functions with the def keyword. Functions have 0 or more parameters as input, and they return one thing. In this case, string is the return type, the output, and person is the single input. The variable name person of type person. So I can get the name and age out of the person using the familiar .accessor syntax. And then I can construct a string here to return, hello person, you're this age, or whatever, right? And that should be name instead of n, you know. Anyway. And in Scala, we don't have to use the return keyword. It's just the last expression in the function becomes the return value. You may, at your leisure, choose to use the return keyword, which I will do later on. So there's some foreshadowing, or more explicit than foreshadowing. Anyway, forward reference, perhaps. So that's Scala 3. You know heaps of Scala 3 now. So an algebraic data type, which is the point of the talk, or I'll call it ADT, not to be confused with abstract data type. When I say ADT, I mean algebraic. An ADT is basically an enumeration of records. What do I mean by that? I can introduce in Scala 3 an ADT using the same enum keyword that we've seen before. So I can say I'm introducing a type called shape. And the type shape has 3 cases, or I would say 3 constructors. So there are 3 ways to construct a shape. You can construct a rectangle by giving it a width and a height. You can construct a circle by giving it a radius. You can construct a triangle by giving it a side. Both of these are doubles, right? These things are all full of doubles. We'll see fancier things later. So I can construct a shape. So this is a variable of type shape, called my favorite shape. Val is the keyword for variable declarations in Scala. So I'm constructing a value of type shape by calling the circle constructor. So circle is a constructor, shape is a type. Yeah? Circle is not a type, shape is not a constructor. The thing after enum keyword is the type, the things after the case keyword are the different constructors. Yeah? That's important. Cool, so that's how we can define an algebraic data type. We can make a value of that type. Let's do some more stuff. So to work with an algebraic data type, we need to consume them. So for that we have a thing called pattern matching. Because really if I, no I was going to skip ahead but I won't. Or maybe I will. Alright. I'm going to skip ahead a bit. So an algebraic data type lets us build types that represent multiple possibilities. A shape could be a circle or a rectangle or a triangle. I don't know which one it is. Pattern matching lets us work with all the possibilities. It lets us ask, which shape are you? And then act accordingly. So now if I go back to where I was. So I can write a function called area, which takes a shape and returns a double. And we use the match keyword to begin pattern matching. This is something like the world's best switch statement, right? We're going to say, shape that came into this function, are you a rectangle? And I've color-coded them here for you. I hope you appreciate that. I've color-coded them. I've said, are you a rectangle? If so, I shall multiply the width by the height and return that. So remember, we don't need return keyword. Yeah? So I've omitted the return keyword, but that's what's happening there. Circle, you know, if we have a radius, we multiply by pi, something like that. It's that sort of thing. Whatever. If we have a triangle, we use some other stuff. You know, that shouldn't say colon double just there, but it does.
Been a long day, hasn't it, George?
Yeah. So.
I have a question.
Yeah.
Does the shape retain knowledge of how it was constructed, and therefore it knows to use the rectangle, circle, or triangle?
Yeah, it knows which one it is. It knows which one it is. And so pattern matching is asking it, which one are you? So we're saying the case rectangle bit is where we're saying, are you a rectangle? And then the WH in parentheses is saying, give me the parts of the rectangle you are. And let me give them names and use them in this expression. You don't have to do a new line for your pattern matches like I have here. Like I've gone case rectangle WH arrow new line. You don't have to do that, but it's often cleaner, so I've done that a lot in the talk, where I can spare the space.
So another word for this would be discriminated union.
Yeah, there's
Maybe with
also,
that from C-type languages.
yeah, discriminated unions. So I can make a circle and get the area of it. Something comes out, it's a double, maybe it's wrong, who knows. This is the slide I skipped ahead to.
I have a question.
Yeah.
If it took in two shapes, like it wasn't the area, it was like, I don't know, some other function, do you have to do all the combinations?
Yeah, it's a good question. That would be one way to do it, yeah. You could pattern match on both of them, and then there'd be like a 3x3, so there'd be 9 cases in that pattern match, or you could do a nested pattern match where you match on one and then match on the next. But typically what you would do is you would define functions that work on shapes, and then build up enough of those, and then hopefully never have to do pattern matching on 2 of them at a time. Maybe if you want to add their areas together, you write the area function rather than doing the double pattern match, if that makes sense. We'll actually get to that later. Yeah.
George, what if I don't want to pattern match on all the ways it can be constructed? What if I just want to pattern match on rectangles?
Yeah, you can do that. I don't have an example of that. That can be done. There's a way to say, if you're a rectangle, do this, and if you're anything else in the world, then do this. Yeah, something like that. Thanks, Donovan. I don't have an example of that. So that's algebraic data types briefly, and now we will look at the consequences of this. Has this ever happened to you? So let's say you've got a class representing some data that your program needs, payment details in this case. I think this is a great example. I don't recommend you writing payment processing yourself. So with that out of the way. So payment details is something like a credit card number, an expiry date, and a security code, something like that. And then we pass this around in our program. And then the product owner comes to you and says, all right, we need a new feature. We need the ability to, we need the customer to be able to pay by bank transfer. And so you go, oh, how annoying, right? So you go something like, okay, well, it's got an account number and a BSB as well. This is kind of the pre-algebraic data type world. What you do is you'd say, oh, okay, well, these things are either all null or all present, and these things are either all null or all present. And Rob's nodding his head really solemnly.
Seen a lot of code like this.
Yeah, I think a lot of people have seen a lot of code like this, right? So, algebraic data types solve this problem dead, right? Very, very solved. Do I even have the fixed version?
Can you tell me why they solved them, George? What is it about algebraic data types that solves this?
Well, we're really kind of shoving 2 possibilities into the same record here. This is really a record that's actually like either this stuff or this stuff. It should be an enumeration of records. It should be a union, a discriminated union of records.
Right, there's no way by construction to guarantee that those invariants hold.
Yeah.
And that's how bugs happen.
Yeah, bugs happen because of this sort of code. So algebraic data types fix this. I've put new lines after commas here, but this is the same syntax that we've already seen. So now payment details is either credit card details with all this stuff or bank account details with all this stuff. Yeah? And now you'd only construct one of these, the relevant one, and then you would know by construction that you have all the things you need, and you also can't have any of the things you don't need. With this formulation, you cannot construct a credit card details with a BSB. You can't even have too much, right? We were complaining about like it's too easy to have too little. You can't even have too much either. You have to have the right amount of stuff. So that sounds quite similar to inheritance. So I should briefly address ADTs versus inheritance. Inheritance being more of an object-oriented data modeling style. So one of the main I would say the main difference between inheritance and the algebraic data type style is that inheritance is open to new subclasses being added. So if you have a class and then you have some other classes that inherit from it, yeah, at link time, right? So compilation happened like last week. At link time, new cases can be added. Yeah? So that's going more into technical detail than I've otherwise gone into in the talk. So if you don't know about compilation and linking and stuff, don't worry. But like you can't know statically how many subclasses of a thing there are, and you thereby can't you therefore can't say which one are you and know that you're capturing all the cases. Does that make sense? You could write code that says is instance of this, is instance of blah, is instance of something else, but then someone can come along with another jar file and link it against yours, and now there's another subclass that your code doesn't handle flying around in your program. So ADTs are closed, so you know exactly how many constructors there are at compile time, and they all live in the same place, typically in the same source file. And if you want to add a new one, you go and put it there and recompile the program. So they're closed by design. And if you forget to pattern match on every constructor, you get a compiler error. We love that. How good's that? I love compiler errors. I hate every other kind of error in the world. Compiler errors are good. So there's more to it than that, and we have to get into more of a comparison of an FP style versus an OO style. To answer the question any better than that, I'm going to leave it at that for this talk. So what else can we do? We can look up a person in a list. So if we have a list of persons, and we want to look up a person by name, we've probably chosen the wrong data structure, but whatever, right? So we can do a for loop through the lists. I didn't want to bring in like a bunch of fold lefts or whatever, and so this should be more understandable to more people. So for each person in the list, if that person's name is the name we're looking for, return the person. Otherwise, if we go through the whole list and that hasn't happened yet, we return null. Right? So this is like the least FP slide in the talk. So this is bad, I would say, because we don't really know from the type that the person might be null. The only way to know that is to look at the implementation. Boo! We don't like that. Right, so we should do better than pervasive silent null. So something like this is what would happen in like idiomatic Java. Let's do better. So we could make an algebraic data type. There's an idea. And we could have person lookup result, which is either person found, and here it is, or person not found. And this would be an algebraic data type for to better model what that function actually returns. Do we agree with that? Do we hate that? Something like that. So I've just put in red the bits that are different in this slide from the prior one, but so now our lookup person by name returns a person lookup result, and it will either return a person wrapped in the person found constructor, or it will return the person not found constructor. So I haven't mentioned this yet, a constructor can have 0 arguments. Yeah. Donovan.
So now I can't compose lookup person by name with other functions that take in people.
Yeah, we won't get all the way to answering that question. But that's a good observation. So this is a good solution, but what if I don't want to look up persons in a list? What if I want to look up payment details in a list? Now I'll need a new data type, payment details result. Either payment details found with the payment details or payment details not found. We've had to, if we wanted to look up a different thing in the list, we've had to create a different type for the output. Boo, we don't like that. Yep. So in order to not repeat ourselves, we have to factor out the differences. And these sort of structural differences, modulo the type name and the constructor names, the key difference between these two things, these two types on the slide, is that one of them, if it found something, it found the payment details. The other, if it found something, it found a person. So we can factor that bit out. Watch this. This is called option. This is a reusable null replacement. So now we have some new syntax. We have square brackets A. Square brackets A in Java is angle brackets A. This is a generic parameter, or I would say this is a parametrically polymorphic algebraic data type. It has two cases, some and none. I think these are bad names, but there they are. So the sum constructor has one A in it called A. The none constructor has nothing.
Why is it not one and none?
Yeah, it could be called one and none. In Haskell it's called just and nothing. I don't think those names are very good either. Whatever.
What are the good names?
Found and not found.
Well, that depends on what the function's for. Present and absent. How about that? Yep. Present and absent. So now that I have a reusable version, yeah and nah, that's a good one, right? And then the monad instance turns yeah, nah into nah. Yeah, we should compiler for Australian English. So now here's the same slide again, the same function written again, but and again highlighted in red are the differences. Now we're using our reusable thing option. We have option of person, and then we're returning sum of person in the happy case. If we found the thing we're looking for, we're returning none in the unhappy case. So this is a reusable data structure. Now if we were returning payment details instead of person, we wouldn't need to create a new data type for each kind of lookup function we wanted to write. So that's good. So we like parametric polymorphism. All right. Any questions about this much before I move on? We're like more than halfway done, so it's, oh. No questions, it looks like. Let's move on. Cool. So we've made algebraic data types for things we like, and we've also made algebraic data types to say presence or absence. We can make algebraic data types to model the different errors that our application might encounter. So if I'm going to fetch some JSON over with an HTTP client, these might be the errors that are relevant to me. Either I couldn't connect to the server, or I got a bad status code, like a not 200 status code, or the JSON parsing failed, maybe I got XML back or nothing. Right? Maybe these are the errors that matter to me if I'm making an HTTP request over the network. So we could return from a function this HTTP response error, but you'll notice that this is kind of only the error half. This doesn't include the good stuff that we want. You see that? This is only bad things. So there's a way to, when people first get started with algebraic data types, this should have been its own slide. When people first get started with the algebraic data types, they'll put all the success cases and all the failure cases all together in one big algebraic data type. This is quite common. So if you are learning algebraic data types for the first time tonight, you will probably go and do that, and then later on you will learn to not do that. Or you could skip it entirely. And it tends to be better to actually kind of factor them out. Here are all the successes. Here are all the different ways we can succeed as a type. Here are all the different ways we can fail as a type. And then we need something to stitch them together. And that thing was mentioned in Donovan's talk earlier. It's called either, or in Rust and so on, it's called result. And result, in this case, has the constructors success and failure. So result has two generic parameters, not one. A and E, I've called them. This is a more Rust-looking one than the Haskell-looking either one. I've either got success with an A or failure with an E. And I can put in whatever types I want for A and E. Success and failure are extremely good names for those constructors because they have the same number of characters in them. Makes everything line up really nicely. So I like success and failure as the constructor names for this type.
I think it makes it seem like the E is inherently bad though. What if you had an A and an E that were both equally okay? Now you have to say one is good and one is bad.
I think that case is much less common than the case that E is actually bad and left and right is ambiguous.
I think having this in a standard library is a sensible and ergonomic choice that will result in better outcomes for that language ecosystem.
Engineers in the language should know that there was in the domain. They shouldn't only exist for the sake of something about those two things.
Right, but Don's argument is that there might be use cases for a type that is structurally identical to this but does not have the success or failure connotation.
Does Rust also have the generic either type?
Not
If I
in a
wanna
standard
communicate
live
that
as
meaning?
far as I know, but you could easily make it. And you might want to do that because reasons.
So let's use this in an example and see how it goes. So if I'm making a call, there should be a quote instead of a colon on there. So if I'm making a request to an HTTP server somewhere that's got some JSON on it, God knows what, then I will get back a result which is either successful JSON or failure of HTTP response error, which is the type I showed a few slides ago. And then what I do, the way I consume a result is I pattern match. Whenever you have an algebraic data type, you pattern match. And then when pattern matching gets too annoying, you write functions that do the pattern matching for you and you call them. Right? And so we've just got this big tower of functions with so much pattern matching going on underneath. That's what a lot of functional programs do. So I've put the match keyword in red, I don't remember why. But this pattern match is asking, did you succeed or fail? And I haven't shown you what we're going to do yet. But if we succeeded, we get some JSON. If we failed, we got an HTTP response error. So if we succeeded, we just print, yay! Right. What do we do in the case of failure? We can pattern match on the error. Because remember, the error, the HTTP response error type that we defined was also an algebraic data type. So it is also subject to pattern matching. So we can pattern match on this. And what I want to, and we can, print line, oh no, or whatever. And what I want to kind of point out here is that each of these pattern matches is asking a different question. Do you see that? The top pattern match is asking, did you succeed or did you fail? And then the inner pattern match in the error case is asking, oh, okay, you failed. Well, in what way did you fail? So a pattern match is usually asking a question. And it can be helpful, especially if you've got beginners on the team who are not familiar with a functional programming style. It can be really helpful to put in a comment like this, kind of explaining what question is this pattern match really asking. So there's the code we had before our technical difficulties. What we can do is we can factor out our nested pattern match. So the pattern match was just for printing out the error. We can factor that out to be its own function called print error. Here it is. And then back where we were, we just call print error. And now we don't have a nested pattern match anymore. So I encourage this, factor out nested pattern matches. And remember I mentioned earlier you should factor your types such that all the successes are in their own type together and all the failures are in their own type together. That's necessary to do this factoring out of the error printing into its own function. So that's like a pro tip for this beginner level talk. So that's looking nicer now, and we've factored some things out. So algebraic data types and pattern matching are now available in a language near you. So you could use an FP type language like Scala or OCaml or Haskell, and which definitely have it, and FP languages have had it since 1973. But mainstream languages have this now, or kind of have it. So Swift and Rust definitely have it. Kotlin and Java 17 and above kind of have it. You can have a sealed keyword. And if you Google Java 17 sealed, a thing will come up and it will tell you that Java kind of has algebraic data types now, and Kotlin kind of has pattern matching. Java might kind of have pattern matching, I didn't check. But we are getting there. 50 years later, and slow-moving mainstream languages now have no choice but to have this.
I have a question. Was Kotlin on your list of modern languages?
Yes, so
Can you take it off?
we'll debate the merits of Kotlin.
C++ has variant.
Yes, I'm sure C++ has this in C++, 11t7 or something. So
According to
We've,
Redmonk, Scala is more mainstream than either Rust or Kotlin.
I'm doubtful of that.
Sorry,
Yeah,
coming
that-
through.
Redmonk. It seems a little surprising to me.
I don't know, Scala has some niche applications in like data stuff.
Yeah.
Like people who don't care at all about functional
Yes.
programming with Scala. I don't know. So, look, I just wanted to throw this in here as like a spicy ending that we can all have a big argument about at the pub. But like, the solution in mainstream languages has kind of been to just invent a new ad hoc thing whenever there's a problem. Like, data might be absent, invent the null reference, right? The null pointer was already there before, so that was an easy one. But like, we need errors to be thrown, right? We need errors to be returned sometimes instead of the good thing. Let's invent throw keyword. Let's invent try catch keyword in the exception class hierarchy. And there are just all these like ad hoc solutions that have become popular over the last like 30 years that are just all algebraic data types and pattern matching that we had in 1973. Isn't that good? All right, that's the end.
I'll only add one thing to the responding to errors row for OO, which is checked exceptions.
Yeah, but no one uses them.
Well,
Especially
you
when
have
language-
you don't have a choice in Java except for some of the lower level exceptions that are always unchecked.
Yeah, I was going to say, it doesn't really work if the language has both checked and unchecked. Like,
Yeah, if you inherit from the right base exception, then you get checked. And in practice, I mean, if you're stuck with Java, it does. Checked exceptions does simulate a result type or an either type reasonably well.
But you can't abstract those.
No, that's right.
Yeah.
And
You can't map over it or abstract over
yeah,
the error
exactly.
type.
Yeah, you lose a whole bunch of
Build
just
generic
innate-
functions that operate
Yeah.
on any.
I
Yeah,
feel
there's-
like it kind of is the same field of debate as the whole return 200 and an error, like from a web server.
Yep.
Sort of feels like it's similar. Because you've still got the whole class of other errors to deal with.
On the errors topic, something I didn't mention in the talk, but I should have, and I can do it now, is I think of pattern matching in a sense as like the ultimate control flow mechanism. Like what makes throwing exceptions really annoying for me is that they have this kind of like secret back channel through control flow, and to the point that it has to become common wisdom to say don't use exceptions for control flow. But like the very nature of exceptions is that they hijack control flow. So like to some extent it can't be escaped. And when you, so in that sense, pattern matching and algebraic data types have just kind of simplified this by having a better, more principled control flow thing. And so many usages of if go away if you have algebraic data types and pattern matching. Like a lot of things that used to be if, and then you had to like squash the world into a Boolean, now become, I can make a data type to talk about what I want, and then a pattern match. And that's the real like juiciness that I wasn't able to put on the slide.
Oh yeah, and it makes not just from a control flow perspective, but Boolean blindness as a source of bugs. Like forgetting what the sense of the Boolean means or what it represents is a huge source of bugs, including security vulnerabilities that you get in programs. So using ADTs and special purpose data types that are expressing the domain meaning of some datum in your program, some byte or word, you use them liberally, you will not regret it.
Yeah.
Let me be contrarian around exceptions. Although, don't get me wrong, I love algebraic data types, including for errors. However, I always miss stack traces. And I wish that my pragmatic functional languages had some, I don't know what it would look like, some sort of syntactic sugar that helped me accumulate easily, by default,
Mm.
accumulate causal information about where an error came from.
Yeah, we kind of have a thing for this in Scala, or Scala has an answer to this, which is we don't use throw to return errors, we use either or result, but we do use exceptions, the data type.
Mm.
And so you can have an algebraic data type where each constructor wraps a different exception. And you can say it's only going to be these 4 exceptions, it's not going to be 26 other ones. And then exceptions, the data type, have all the stack trace niceness, and you're getting your algebraic data type pattern matching, they're not doing... So like throw keyword is much worse than exceptions, the data type, in my opinion.
But that still requires your programmers to be a little bit disciplined about making sure your error types communicate which part of the program they came from.
So
Yeah, yeah.
Is there like a macro that where you have functions that return an exception that it actually updates that exception value to the value?
Yeah, something like that. Something like that.
Okay, that's.
I mean, to some
that's
extent,
fancy.
like, I mean, it requires discipline to do any of this in Scala, right? Like the,
Yeah, sure.
yeah, or Kotlin or whatever.
So in inheritance, like object-oriented libraries, there's like stuff like Harmony, which it's a layer of persistence for your class, and you can chuck it into a database. Is there something similar for ADTs, or do you just use the same type of thing? Like,
I think it depends what you mean by similar. I don't know, let's talk about it at the pub. That's enough questions for not eating dinner.
Thank you, George.
Cheers, George.
cheers, mate.